So down under, it's just because we're literally like on the other side of the planet, where we're already on 28th of April in the morning, still dark. And the thing that I wanted to talk about, I would just, first of all, thank you very much all attending. Unfortunately, I cannot see any faces. Apart from Marino, I know you and I know Ian. Everyone I don't know, and I cannot see anyone. And I also don't know exactly what you guys doing and what is your scientific interest or instrumentation interest. And also, so what I was assuming you don't know much about what's happening in Australia in terms of small angle scattering. So I thought to give you a bit of overview of what we've got here. I mean, Bilby, one of the small angle scattering here, it's my instrument which I built, which is called Bilby. So of course I can talk about Bilby for like half a day if you will not stop me. But I thought again, just try to get a bit wider and just start from, just really tell you what we have. And if you need more details, always welcome to talk later on. Now then, I thought about very special first slide. It didn't happen. First slide is very basic because again, I just wanted to kind of start from very, not going to go to any theory. I'm not going to talk about any specific deep kind of things today in terms of science. But the only thing I just wanted to mention in the first, so again, I would assume the most people here are X-ray users, and we talk about neutrons as well here. But also I know that some time ago you got a seminar about Will Heller, who was talking a lot about neutrons and their properties, so I'm not going to repeat that. The only thing I just want to mention again, so you know perfectly well what X-rays are doing in small angle doing, and the feature of neutrons, just they are complementary to X-rays, and they have no charge and have, but they have spin. So basically, what we will see later as a kind of examples of science we can do with those neutrons. So a couple of things we're using a lot. We're using the thing that they're not penetrating, or they're penetrating very well. They're not damaging the sample. They have spin, so they're very sensitive to magnetic structure. And another thing which is pretty cool about them, and also pretty cool about our facility, that as we know, neutron scattering ability, the scattering length density of material is really depends a lot on the isotope form of the material. So scattering ability of hydrogen and deuterium, for example, dramatically different from each other. If you see the numbers, they're just really huge way. And what it gives us, so if we have material to study with neutrons and we want to replace, for example, hydrogen by deuterium, we're really changing the scattering ability a lot. And to use this actually, so it sounds perfect in theory, but in practice to implement it, you have to be able to replace that hydrogen by deuterium. And we have facility, I will mention it a bit later once more, we will have facility at our place at ANSTO, deuteration facility was actually able to do this. So we're not just doing the neutron scattering, we're also able to prepare material which suits better and try to, opening more possibilities for this thing. All right, so this is just like where you're starting from. And another thing which is quite interesting, our facility here, it's not just SANS, we also have SAXS instruments. So I'll try to cover as much as I can. If it will be a bit jumpy and too dense, sorry in advance, but I think it's pretty cool to show. So this is where we are now. And this is Sydney on the top of the nose of the scat. And then, interesting thing to say, Melbourne Synchrotron also, which is in the month, this is also part of ANSTO since some time ago. So ANSTO stands for Australian Neutron Science and Technology Organization. But again, just political or strategical decision for a few years ago was to add Australian Synchrotron to that facility, to that umbrella as well. So, and I just tell you a couple of words about both, and then I will focus more on SANS. Right, so if now we're staying in Sydney and speaking about reactor and neutrons, so what we are? We're a facility, I think like all of us, middle of nowhere, surrounded by bush, with snakes, spiders, full Australian setup is there. I'm not joking, we have snakes at the building, in my steps of my buildings from time to time. But nonetheless, it's a very nice location because it's quiet. It's about 30 kilometers from Sydney City, not too difficult to access. ANSTO by itself is huge. We have several different divisions, and I'm not sure that I'm going to go into details of all of them. It's just too much. And I will just focus on our reactor. So we have like open water reactor, which is just like we take, again, it's only part of ANSTO as such. And another thing, I should say, so our part, which is neutron scattering facility, it's only part of business which ANSTO is doing on this reactor. Just to mention, again, I leave it to you to look it up if you want. We have neutral activation analysis using reactor. We have pharmaceuticals, medical supplies produced using reactor as well. We have silicon radiation facility. So basically, we are maybe the most scientific one, which not bringing much money or bringing a lot of science and knowledge into this place. Right, so we're kind of focusing more and more on what we are. Just out of interest, maybe, so we are 20 megawatt research reactor. Again, OPAL compact core, low enriched uranium fuel. We're operating more than, what we are now, 14 years in operation. And yeah, it's lifespan of reactor gonna end in like 2055. So this is just very fancy photos. I think everyone like the blue water, blue light water things. So this is our little reactor. And we are very ambitious in terms of the request for this reactor to run. It's about 300 days per year. I mean, guys who work as instrument scientists, I think you can imagine what it is. So that's pretty intense. And for some time, it's been going like that. It was, of course, it's been some drops from time to time for different reasons. Cold source was not behaving here and so on. But 300 days is quite intense. Right. So, and now kind of going back like more to a bit more science. Oops, sorry, too much. So yeah, fine. We have a reactor. Somehow we have to get neutrons, and I just have to get some instrument on this place. So what is actually giving us neutrons? So we have thermal neutron ports for things like diffraction and single crystal. We have cold neutrons. We have thermal, again, another port and another cold and thermal. So the arrangement of that, it's basically, why it's arranged like that, it's usually made, it's just design kind of, it's a design properties which with attempt to give as much neutrons out of a reactor as possible, considering also spatial distribution. So if you have cold source sitting somewhere inside, there is only certain places you can get the cold neutrons out and so on. So when you're talking about thermal cold, why it's interesting, so you see, so it's the same kind of thing, but in a bit more schematic view. So just again, just about our instruments. So what is interesting here, sorry, just now it's all, yeah, here we go. Again, for people who don't work with neutrons, why we're talking about thermal and cold. The thing is, thermal for us, different physicists use different words for different energies, just by habits. So for us, thermal will be about maybe up to 2 angstrom neutrons, maybe 1.5 angstrom. So we're speaking angstroms. And cold will be between 2 and 20, 2 and 25 angstroms. The difference, so why we need different ones? Because different techniques demand different energies for the sake of looking of the material of different dimensions. So basically, again, diffraction and cold, diffraction and single crystal will require, they're looking at atomic distances, they need shorter wavelengths. A small angle scattering reflectivity needs bigger one to look at the larger one to look at the big objects. And we have a couple of ports for our instruments on the other side. So this is like how we work. Right, forget about this one. Now we're kind of focusing more and more now, just like crawling slowly to the small angle scattering. And what we've got, small angles, we all know the longest one. So it's pretty cool because they are always the most visible. I mean, maybe I just like attention. So for me, it's very comfortable when everyone see my red instrument. You know, it's Bilby. Quokka there as well, Kookaburra, and we have also X-ray, little tiny X-ray, lab-based X-ray machine. I think I'm just using all those very strange words as the names. Sorry, I forgot to put pictures in. But as a tradition for ACNS, so we call the Australian Centre for Neutron Scattering as a part of ANSTO. So all our instruments called after Australian animals. The animal itself has nothing to do, nothing similar to the technique it's used for. It just happened to be like this. So basically, echidna, I think it's like big hedgehog. Wombat, it's just like little, I don't know, fluffy piglets, maybe, no, guinea pig, a massive guinea pig, massive. and so on and so on. So Quokka and Bilby, it's kind of mixed between rat and kangaroo in different proportion. Bilby a bit smaller, Quokka a bit bigger, Kookaburra is a bird. So again, it just name, and again, maybe it's inconvenient, sorry for that, but basically it's small angle scattering, small angle scattering, and ultra small angle scattering machines. And as I said before, synchrotron also is part of us. Now, again, for the sake of interest of people using SAXS, I just show you very briefly what we have on synchrotron and will not go back anymore. So just let's just sidetrack a little bit to the Melbourne. So just jump into the Melbourne very quickly. And this is information, again, you can look it up further if you wish. Just now to get you a very brief idea what we've got. We've got absolutely wonderful SAXS machine, SAXS, wax, beamline, and synchrotron operating. Nigel is the main person to do this. I'm pretty sure majority of you know Nigel. So have some characteristics of the machine. It's very, very nice one. And again, working steadily for a while, a lot of automated setup, perfect flow sample, perfect background subtraction, a lot of kind of very convenient things for users in terms of data reduction on the go and so on. So this machine is really, it's a really good piece of work. So again, this one, so one SAXS wax in operation, another one coming online maybe in a couple of years. So it's BioSAXS, and Christina, she's the main person who is running the project to build it. So this machine will be maybe a couple of years away, getting good shape, but work in progress. And also I have some links here, which again, when the presentation will be uploaded, you can come back and look them up, or you can just Google SAXS and BioSAXS on Australian Synchrotron, and you will find it. So again, this is just a bit of sidetrack to show you how well we are equipped in this country. It kind of sounds far away because Sydney and Melbourne, it's like 1,000 kilometers away. Like Australia measure, it's next city, right? So it's our neighbors. Flight is a bit more than an hour. So it's quite handy when you can get both instruments into your hands. But only just consider, so user access for both of us are very separate. So beamline proposals for synchrotron and neutrons will go separate ways. But again, instruments are available. Okay, so that was a bit of sidetrack to SAXS. And now we're traveling back to Sydney, and we're staying in Sydney from now on. Where we have in Sydney, we have neutrons. And again, now focusing even a bit more into our instruments in details. Just tell you first that, again, as I said, we have two, oh my gosh, that should be blue as well. We have two small angle machines, USense, and lab-based SAXS machine. Yeah, just for convenience, because Melbourne, yes, close enough, but not as close. And we have several people working in our group. So we have Elliot and Katie working on Quokka. We have Charlie, who actually shared his time between time of flight machine, like spectrometer, and also a bit of Quokka, a bit of Bilby. Lela works between Bilby and Kookaburra, and Jitendra works on USense all of the time. And myself and Andrew work only on Bilby. I don't know how people can share. I think we have enough on one. So good job for them. Right, so this is our team. Yeah, here we go. And again, as I mentioned, we have a little lab-based SAXS. This is a very new one. It just been commissioned like 3 weeks ago, and it's waiting for its license to be able to use for users at our facility. It's literally sitting like 10 meters away from Bilby. This machine, as I've seen from training, is just wonderful. It's really great. I know praising things a lot, but I really like them. And Robert Knott is in charge as instrument scientist of this little one. But the kind of catch is that this machine can be used only as a part of neutron proposals. So we're not accepting proposals only for SAXS, but if you want to do complementary SAXS with doing SANS at the same time, this is where this machine comes into play. That's a bit of political and a bit of, you know, how the system set up. So yeah, here we go. Now kind of starting from very small angles. So now I just kind of give you a couple of words about SANS instruments themselves. So starting from very low Q, we can access, we have a USense machine. It's a double crystal, Bonse-Hart instrument, which is, I would assume, pretty standard, pretty well-known configuration. And I think the main feature of this one is that it can work with two wavelengths. So it can work on 474 and 237 angstrom. It's monochromatic machine. And just the thing is, if you want more flux in certain Q accessible, you will go to the 4. This is how spectrum works. It's more neutrons at 4, but sometimes you have multiple scattering in that range. But if you want to kind of make things a bit sharper and shorter to reduce multiple scattering, then you go to the 2. So that's pretty flexible. Considering setup, I think it's very flexible and it's very well used. So lately, actually, it's picked up a lot on the user demand. So it's pretty popular instrument. Because a few years ago, perception was like ANSTO will never be popular. Haha, not the case anymore. Right, so that's SANS, and now getting a bit further down in Q range, we're finally coming to the SANS. So as I said, they always look impressive because they're big on neutrons. So Quokka is one, and Bilby is another one. Talking a bit about the features. So Bilby was commissioned in 2015. Quokka was commissioned a few years earlier. So we're like kind of younger sister of Quokka. Why too? I think all of us knows why we need more SANS, because it's always oversubscribed. And also when we had project to build Bilby, it was question, what are we doing, which will perform very well, but will be different from Quokka, just for the sake of covering a bit more science. And what we've done, so Quokka is monochromatic instrument, but it can have polarized neutrons. It has polarizer up there. It has lenses, so it can go to the focus neutrons and go to low Q. But Bilby actually using choppers to beat time of flight, and I'll tell you a bit later why. We can, because of that, we can adjust resolution, wavelength resolution, and also because of that, we can have massive Q range. So those Q ranges, they're accessible Q ranges. They're not Q ranges you can get in one go. I mean, that would be awesome, but but anyway, so accessible Q ranges. So just get a bit deeper inside. I'm not gonna, again, this is like my favorite thing to talk, so I cut myself short here, just to tell you one thing. Again, it's the same thing, just a bit more insights, just to show you that Quokka has one detector, but Bilby has two. So we have red detector, which is square, it's a tubes. And we have curtains, which is 4 panels, and those panels, curtains, those here are, they can move up and down and left and right to cover massive Q range again. So we have choppers plus massive coverage of with detectors. And again, yeah, Quokka has polarizer and lenses. So this is like the main difference. But again, I should say, every instrument scientist will say that the instrument is the best. I mean, I haven't met anyone else, anyone saying differently. But speaking practically, of course, the mainstream scientific task, both instruments can perform very well. So it's really a kind of, so kind of features which are different them from each other, they're making each of them unique. But for mainstream, it's really, you can do both, which making it probably difficult when you submit proposal because you have to select the instrument. And how to select instrument for something which is kind of mainstream, you just choosing basically with whom you want to work as instrument scientist. But also actually I had to say that despite of having choppers and time of flight option, we also have velocity select inside. So we can use either or actually we can use both for some very interesting setups. Right. And also, but because I like to praise our instruments and say how great we are. So Quokka has absolutely wonderful new detector, which is like little pins, about 5 millimeter separation. For 5 millimeter for SANS, I know for SAXS it sounds like seriously, but for SANS instrument, 5 millimeter separation between points, I mean the pixels on detector, it's very tiny. So which means I have to cover a lot of Q range with a lot of details. I mean, spatial resolution is wonderful. And this detector can handle a lot of flux. And this is like an example of 1 second data, 10⁻⁵. So just like how great it behaves. So yeah. All right, fine. One thing which I really want to say for people who works on spallation source or reactor or X-rays, just to say basically why we are making spallation source instrument on reactor and what's the point. The point is quite simple. So if we have neutrons coming through the reactor, the entire spectrum comes through. This is spectrum given to us. It's like from 2 to 20 angstrom, like the entire thing. If we have, and there is no time structure, so we don't know which wavelengths are coming. If you select velocity, if you take velocity selector, selecting one wavelength, you are sorted, right? You know your wavelengths, you are done. If you want to use a lot of wavelengths, you set up something to select the whole lot, but then you have to know what are those ones, right? So sorry. So to know what are those ones, what we are doing, somewhere in the chopper system, we have point, this mouse is horrible. So we have a point which we define as origin of time. So somewhere we have origin of time. Not going to go to details now, but the point is we know where time of flight starts, and then we measure in time of arrival of the neutron detector. And this is how we're doing this. So once we know time, we know the velocity. Once we know velocity, we know the energy or wavelength. And the point of that, I think I just even mentioned before. So if we have a lot of wavelengths, we have a lot of lambda here, we have massive dynamic Q range we can measure in one go. And the benefits for that will be majority of us, why we are very special in experiments like kinetics. Because Quokka, for example, instruments like Quokka with one detector and one wavelength, they can still cover a lot of Q. But to do this, they have to measure, they have to collect scattering pattern at separate different distances of detector from the sample, which means you have to stop measurement, move detector, start again, stop, start again. It's wonderful for samples which are not going anywhere. But if you have sample changing with time, like kinetic experiment, you really have to take snapshot all at once. And to have the snapshot all at once, it's wonderful to have Q range with pretty large, which means a lot of wavelengths, and having massive detector setup, a lot of CT as well. So this is just how, this is the reason to kind of go to all those complications and make this very special time of flight. We're not unique on that. Bilby is it's very similar to D33 at ILL, just to say, in design. So, but both of them works, and both actually of them quite similar to reflectometers instruments. But concept is there and it works. Right, and another feature which is different from spallation source to what I know, I mean, you can tune on all instruments and make them different and interesting, but for us, it just comes for free in a way. The thing is, what is this thing is? Just to tell you in short, so we have set of choppers, playing with the choppers, to setting up choppers which giving me pulses, I can play with wavelength resolution. So this is another quite unique feature of Bilby, where we can not just get a high Q range, but also we can play with wavelength resolution. Of course, this beautiful thing doesn't come for free, because if monochromatic instruments working mostly of 5 or 6 angstrom, with 10% resolution roughly, when we have the same 10% resolution on our machine, our flux is at the level of 8 angstrom of monochromatic instruments. So basically our flux is a bit lower. So we might, which is actually not big drama for well-scattered samples, but for weaker samples, we have to consider this thing. And also, again, not going to many details, the only thing to say that if we're going through voice resolution, if we're relaxing resolution of wavelengths, we have more flux. We're tuning it to very fine one, we are losing flux. So again, just have to be really careful with these things. Don't request some kind of, I want perfect resolution, I want like everything kind of work very tuned. For the samples one, you don't need it because you will lose a lot of time. If you have very simple kind of, expected very simple data set, don't bother, just open up resolution and don't forget about all this. You don't need it, but you will have a lot of flux and Q range anyway, just as a tip. And just to show how it looks like. So this is the difference, just very standard. It's our example from paper, how better you can resolve peaks tuning resolution to like 6% or 5% here versus 10. And this is difference. So it's the same detector setup, monochromatic mode and time of flight. You people who works with neutrons might say like, the high Q is always complicated for time of flight with hydrogen because hydrogen has a massive incoherent background plus inelastic incoherent, so it's a lot of fun there. It's true. So you just have to know sample quite well to expect something fancy in high Q. But it's just put this. All I want to say here, we know there are some other complications and things with time of flight, but also we know how to deal with them. But a nice picture, a nice message is this one. So yeah, here we go. Again, I leave this slide just to look up for later, but this is what I want to say about the instruments. And now I just wanted to show you very briefly what kind of science we can do, just maybe to impress you. Just nice pictures. So now we kind of know we have instruments, but it's all fine, it's entertainment for us, but the main point is what we want to do for users. For users, we have, as I think any facility would say, so we have a set of sample environments which users can demand. We also have a chance to help users to develop their sample environment. Depends on availability, so have to start conversation in advance if we want something nice. But look, we're quite well equipped with temperature control. This is what here we talk about soft matter. Temperature control tumblers, especially for USANS, tumblers are important when you rotate the samples, not letting it sediment. We have a rheometer, which is cool, stop flow cells, and so on and so on. So we have quite a set of things, and all of them listed in our document online. And just to give you a couple of nice pictures just to show what we can do. And also actually highlight one thing. I kept saying we have several instruments. And this is the point that quite often we have proposal merging both. So this one, it's from Kookaburra and Bilby. That was the surfactants, which has some hierarchy in the structure. And this is classical example for us already now, classical, like since like 4 years, classics. When we can combine Kookaburra data, USANS data, and SANS data, covering the whole lot of dimensions, and therefore kind of to kind of zoom in into the sample or zoom out, depending on how you look at this, to see the hierarchy in the instrument. So this is perfect example for that. Rheometer also very cool thing for us because again, clear why. So you can see the sample and just see evolution of the sample. And a nice example of this work was done some time ago when we got a library of surfactants. Again, don't go deep. I'm not going to go deep to any scientific case here, just really to show you what we can do in like very nice, wide way. So again, it's the same logic. And then because we're pretty intense instrument and we can accommodate, I mean, we can really fit in a lot of measurement in 4 days for the samples which scatter as well. So basically this was a very nice example of kind of scrolling through the massive library of surfactants and see how they're changing with different ads and rheology as well. So this is just typical work we can do on the instrument. This next one, this is very complex project, but again, this is more like tick box for those ones who wants to dig deeper. Because again, like look up those links if you're interested in this particular type of work. Liquid crystals are bread and butter for the high resolution SANS. Again, for those of you guys who work on SAXS, looking at those peaks, you might say like kind of, I mean, seriously, they're not well resolved. Again, for SANS, they are. So, and this was working on the liquid crystal and the proteins, little proteins crystallizing inside the matrix. And here the complication was, remember we talked about contrast a little bit, we talked about substituting hydrogen by deuterium. And here work was so precise because look, so it was this molecule, it was the matrix of the monoolin. So it was the matrix of those peptides or proteins to crystallize inside. And the interesting thing was how to build this matrix so it will not scatter. To build this matrix to be able not scatter, you have to replace some hydrogen by deuterium. And it was a lot of work to find this little kind of orange condition, which was just part of hydrogen replaced by deuterium, which was great work by our titration facility. Because if they were trying to replace the whole thing, it was out of range. If nothing was replaced, it was just massive scattering. If you have like tiny little peptide crystallizing or protein crystallizing inside the matrix, somebody is talking together with me. Sorry. Right, so the point is, again, so a lot of work to just create the matrix which will not scatter, and then actually it appeared that a problem was that matrix by itself was actually changing structure with time, without even peptide. And then again, I'm not going to deeper, but a lot of work has been done. So considering the matrix itself, put peptide in and watch how it's crystallized, how it's getting crystallized in that matrix, basically doing SANS at the same time. So that's, yeah, so that's the, again, example of why you need to bother with high resolution data. Right, this example just a bit for entertainment, because I think it's pretty cool. It's a bacteria, it's next example. It's a bacteria, it's cyanobacteria, which has this photosynthetic mechanism inside them. And in this kind of structure, like ordered structure, it's depending on lighting. So when it has light on them, they're growing those things inside them. When there is no light, they all like dissipates. It's pretty nice. And why we need neutrons here, just because we could grow those bacteria in D2O, so a bit of more kind of enhanced contrast. And again, systems like that, they're massive. They're such massive as well, right? So it's entire living system. Whatever is in there scatters. But having a system like that is kind of lucky because you know that the only ordered system, this ordered kind of component is component you want to look at. Once you have this order, you have your peaks, and then you can analyze them basically without bothering too much what else is in there. So it's really very nice to focus all you want and kind of ignore all the rest. Appreciate, but ignore all the rest. So anyway, that was fun one. All right. Going to also a bit more complicated system, the very fresh work which been done on few instruments all together. That's a system where the guys were looking at the basically the digestion of protein, imitating like stomach system in the beam. So just pumping this the casein, it's a main component of milk, pumping this thing through the system in the beam and just see how adding whatever adding here, pepsin, it's one of the main of digested peptides in the stomach. And we're just looking how the structure of casein is changing in situ, basically. So that was also quite fun. Right. And in the last probably example, I think it's last one, for the soft matter, it's a thing which I really like personally. I think it's the most elegant thing I've seen. So what they're looking at, so they're looking at alpha-crystallin. It's a very complex, multi-dimensional, multi-unit protein. And it was really interesting to understand if this protein sitting by itself in solution, really having those units interchanged. And how they've done it, so they've got one portion, just some amount of this protein hydrogenated as it is, and then the same amount of deuterated. And what happened, if the idea was, if the units start to interchange, at some point it will get to equilibrium. So, you know, both of them will have both hydrogenated and deuterated. But in terms of SANS, it would mean that scattering, at first, we've got a lot of contrast scattering, but with time, it will disappear. And this is exactly what happened. So it's just really, once you go to the middle, they've got perfect like disappearance of scattering, confirming the idea that units are really interchanged. So it's really fun. So you have the same material, but kind of coloring in differently. You can watch what's going on there. So it is, yeah, fine. When we're getting closer to the finalizing thing, and just a couple of words about hard matter, because Australia, it's quite heavy industry country, I should say. And it's really keen on metal work and geology. Therefore, hard matter, even in SANS, is actually getting popular, because usually people think SANS is only soft matter. And I personally was quite keen to check what we can do for hard matter. So it's not my pure scientific interest from my university, but it's just quite interesting to see what instrument is capable to do. And also, of course, learn on the go what the materials are. Sorry, somebody's not muted.
Shall I just...
All right. So magnets crystal at high pressure, classical thing. And another thing which I learned, is, which was impresses me, for SANS, some samples, when we're looking at some feature, they are of dimension of 2 by 3 millimeters, and they still scatters quite well. So really, when the kind of having the instrument appeared to be very important, and we do have it, just all sets of apertures and all sets of way to collimate beam very small. Though intuitively for me, it was just like, seriously, like 2 millimeter sample, but apparently it works quite well in some situations. Right. Just an example why time of flight quite interesting on hard matter. This is example to study steel. Not going into many details, but one thing to say, steel quite often works like magnetic matrix, which is iron, and some non-magnetic impurities. So something non-magnetic in magnetic. Neutron contrast is there as well, because they're chemically different compositions. But again, as I said before, neutrons have magnetic moment. Neutrons are sensitive to magnetic features of the element. And when we're working with steel, again, we're having like magnetic and non-magnetic matrix. And we are able basically to distinguish between magnetic scattering. So we really can say quite a lot about impurities size distribution and like sizes, yes, okay, fine, size distribution of the impurities in the sample, looking on both magnetic and non-magnetic components. And this is just a typical shape of scattering So we're getting ready to two-dimensional scattering. All I want to say, because it's not symmetrical, what it means in one dimension we have only nuclear scattering, in another dimension we have magnetic component involved as well, which gives us a lot of information about those impurities. And the thing which I really appreciate now in time of flight, look, those of you who work with metal will know this thing quite well. It's a break edge, it's an effect which is called break edge thing. So what it is, it's some wavelength, so this transmission, right? So this our entire spectrum, transmission through the sample, and you can see some kind of step in at some point. What is this? So it means that for kind of semi-crystalline material like metal, you have some wavelength, some neutrons, they experience like the whole back reflection. So it's they're not going through, they're just kind of reflected back through your sample, and this gives you that deep. So it's called break edge. And when you have time of flight, you're actually capable to look at this transmission itself and actually get some information about your material itself only from transmission measurement. It's pretty nice. Japanese people, I can't remember the name of the group, but Japanese people use this thing quite a lot. Another thing which kind of, speaking skyrmions, it's just another example of how great magnetic properties of neutrons are. So what it is, again, not going to deep science, but just tell you. So in very simple words, for those who don't know, some materials, you have to have single crystal. So you have to have very well ordered material, single crystal material. In this case, it was this one. What it does, all atoms have spins. And if you cool down this material and apply a field, you're actually making those spins arranged very nicely. So you're making, on top of crystal structure of the sample, you're making crystal structure of your spins on top of it, like magnetic moments. And if you have your neutrons shooting on it, you are sensitive. So you're able to solve or get diffraction pattern, if you wish, of that arrangement of spins inside your sample. So it's kind of, so it's therefore skyrmions is actually a topological spin structure as it is. You have to be quite careful where you want to sit. So this is just an example of nice picture, this example of another nice picture. You have to be quite careful where to sit to find them, because for this sample, this experiment I was involved, so I was doing it with my collaborators, that was about 2 Kelvin, and with the field like well under 1 Tesla, like 0.1, and like around way below 1 Tesla. So this is 2 Kelvin structure. Here we have 28 Kelvins, 12 Kelvin. So again, it's quite cold. It's much warmer than here. It's a different condition, but still it's very cold. So to play with those structures, you have to know phase diagram of your material quite well, and just keep in mind. So there are some skyrmions exist now at room temperature, but they're quite unique and special. But to get like more classical skyrmions, you have to get cold in the field. But it's still perfect. And again, sample sizes for those ones, this is like really tiny, tiny thing. And this scatters perfectly well, if you know where to look. So that's, for me, this is a beautiful example of deep science and like deep kind of, this is the only neutrons can do this. Nothing else can get to that particular information. Similar goes to superconductors. Again, not going deep in science, the same logic. So you have to know what to do with your material, which is superconductor. And basically what's happening, so you have so-called flux lattices. When you put superconductor in superconducting state, you have some kind of magnetic, very simplifying, lines going through the sample, and then you have little currents going around to compensate it. And so you again have kind of crystal structure, which is kind of magnetic crystal structure inside your sample, shooting neutrons on it. You can see how it changes, how it reflects, being kind of nearly diffraction pattern again. And the last thing, which is very exotic example, I just mentioned just above that we can see study metals, it's a sword. Study metals, we actually can see the transmission and we can see break edge. And that particular work was pretty special because guys here were studying the structure and imaging of those swords, but on small angle, we were able to see the transmission quite well. And actually they made some conclusions of the material of type of iron and structure of iron inside the sample. All right, not stretching your patience much longer, just going back. So if you want to know more, we are pretty well published. You can see it all. If you want to see more kind of statistic in where we are in the world kind of arena, this is some kind of statistics for you. You can come back to the presentation later to look more details if you wish. But again, all I wanted to say here that we do have 300 days, therefore we are capable to do all those massive science. We have 2 deadlines for proposals. And yeah, this is some distribution of the subjects. So we see quite a lot of soft matter, bio, and then a lot of materials in engineering. This is for entire CNS, it's not only for SANS. A lot of proposals for different experiments. So Quokka, very well-known instrument, have a lot of demand. We have a bit less because I think people, I don't know why, honestly, maybe because we are young and not people know about us, but we're working in this marketing. But both of us together have quite a lot of proposals submitted. Sorry, here we go. But yeah, here we go. This is the demand from the last round, but we are there. And we are international. Speaking of, if you ever want to think about submitting proposal with us, come along, because we have, again, we'll have a lot of international people coming to us. Visa and clearance, security clearance takes some time, so better to, you know, think about those things in advance. But speaking of proposal submission and talking to us about experiments, don't have any limitations whatsoever. So we're absolutely welcome to come to work with us. You are not paying for instrument for the time if you are coming with normal proposal and want to publish results. If you have some PhD students who are really dying for the data because they're finishing the work and need beam time really urgently, and you can justify that the beam time will end up in publication, you can try to submit proposal, talk to us, and try to submit proposal as discretionary, so which means not waiting for the deadline, but it's pretty special cases. And the only people paying, it's commercial users. Commercial users are not expected to publish, so they can just measure what they want. So we just have some safety requirements to their samples, but otherwise we don't need to know much what is in there scientifically, unless they want to do it by themselves, but they pay for beam time, but they're not publishing the data. If commercial people come in and want to publish, then it's more kind of normal proposal. And speaking of commercial, we have heaps of people working with us on, this is not only SANS, this is the ACNS altogether commercial clients. And on this, actually, I'm happy to conclude. Thank you very much for your attention.